but I'm back to resuming after a little break. So I did, in the meantime, write a couple formulas for total models that I missed because ChatGPT and DeepSeek did not go over those. But I did find it in um, the chapter reviews from before, and I'm not sure if this is going to make it to the final, but it's better to put it anyway. So for the MALO-CP formula, for a fitted least square model containing D predictors, the CP estimate of test MSE is computed using the equation. I don't know if it's important to write just the formula or to write the fitted least squares model containing D predictors of the test MSE. Let's put the formula first. CP is 1 over n times RSS plus 2D sigma hat squared, where sigma hat squared is an estimate of the variance of the error epsilon variance E. And it is estimated using the full model containing all predictors. Hello, Krishna Boyar. Welcome to the stream. CP Statistics adds a penalty of 2D sigma squared hat to the training RSS to adjust for the fact that the training error tends to underestimate the test error. Baby, see face you. Sorry, I don't show my face on my streams. I mean, you can't expect much anyway for someone who just studies all day. Like, just imagine that. And yeah, the penalty increases as the number of predictors in the model increases. This is intended to adjust for the corresponding decrease in training RSS. Hello, Payday Legacy Roblox. Welcome to the stream. CP Statistics tends to take on a small value for models with low test error. So, when determining which of the set models is best, we choose the model with the lowest CP value. Lower the better. Because what? Why? Because that means low test error. We want low errors. So the AIC is a cake information criterion. I'm Russian human. Nice. Russian is cool. I don't really know much about Russia though. What are some things that you wanna teach me about Russia, as someone who has no idea about anything about Russia except for the stereotypes, like they're good with large wild animals like bears and tigers. The AIC criterion is defined for a large class of models fit by maximum likelihood. In the case of least squares with error terms satisfying the 4 assumptions, maximum likelihood and least squares are the same thing. In this case, AIC is given by Man, all my pens are so bad. Let me get another one. So AIC, oh my god, no, this one too. This one better work because it's brand new. AIC, one, oh my gosh, no, this one too. Wait, 1 over n RSS plus 2d sigma hat squared. I don't know English that well, but a translator sometimes helps too. Good luck with your development. It's time for me to go. Okay, thank you so much, Russian person. And I hope you do well in whatever you're working on too. And thank you for joining the stream. And your English is good, even using a translator. So note that for the least square regression, AIC and CP are the same, omitting constants from each term. And then the BIC is the Bayesian information criterion, and it's derived from Bayesian point of view. What is Bayesian? Bayesian inference is a method of statistical inference in which Bayes' theorem is used to calculate probability of hypotheses. Yeah, I guess that's a person's name. In least square regression, I'm gay. What? Are you a guy or a girl? I mean, I don't think you're gay unless you're a girl. BIC is derived from, wait, in least squares regression, it ends up looking similar to CP and AIC. For the least squares model with D predictors, the BIC is up to irrelevant constants. You're both? You gotta choose one. 1 over n RSS plus log n d sigma hat squared. So the BIC will tend to take on small values for a model with a low test error, and so generally we select the model that has the lowest BIC value. Wait, let me read that again. So it's the same as the CP. It's like the difference is when the 2 in AIC is replaced by log n in BIC. So since log n is usually larger than 2, the BIC statistic places a heavier penalty on models with many variables, and hence likely will result in the selection of smaller models than CP. So, n being the sample size, I don't really get that, but hopefully that's not important for the exam. So, I just did r squared. Recall that the regular r squared is defined as 1 minus RSS over TSS equals 1 minus y. I don't think I would understand that in the exam if I looked here. All over summation yi minus y bar squared. And then for least squares model with d variables, the adjusted r squared statistic is calculated as, hey, where'd that guy go? RSS n minus d minus 1 all over TSS n minus 1. Oh, divided by n minus 1. Okay. For the least squares. Okay. So unlike all of these, a larger value indicates a model with a small test error. So maximizing the adjusted R squared is equivalent to minimizing RSS over n minus d minus 1. So while RSS always decreases as the number of variables in the model increases, adjusted R squares may increase or decrease due to presence of d in the denominator. I don't know if that's important to know. Let's see. Okay. Bruh. Okay, so in the forest, by selection, we gain a sequence of models, intercept only. How to choose the best models from the candidates. Top row consists of the best model with forest selection models and based on BIC. So we have intercept, this one, hits, walks, CRBI, division, putouts. Okay, no assists. Okay, got it. Validation and cross-validation. So, in addition to all of these discussed before, we can also use the validation set approach or cross-validation to directly estimate the test error. We can compute the validation set error or the cross-validation error for each model under consideration, and then select the model for which the resulting estimated test error is smallest. The advantage relative to the forest statistics in the previous section of validation approach or cross-validation is that they provide direct estimate of the test error, make fewer assumptions about the true underlying models, can be used for statistics. So, let's see. Advantages of CP, AIC, BIC, and adjusted R squared are direct estimate of the test error, number 2, makes fewer assumptions about the true underlying models. Number 3, can be used in a wide range of model selection tasks, even in cases where it is hard to pinpoint the size of the model or to estimate the variance of the epsilon. That's a large way to put it. Where did everybody go? Am I over streaming? I can't over stream. Is it a good idea to stream whenever I study? Alright, so number 3 can be used in a wider range of models. Even if cases where it's hard to pinpoint the size or to estimate the variance of epsilon. Okay. Disadvantages: computational cost for performing cross validation is very high. Alright, and then the arcand for the validation split is train creates a vector. Best subset selection. Validation for each of the 19 models acquired on the training set. I evaluate the error on the validation set. Okay, then find the model size P that minimizes the validation error. And then finally fit a model of size P on the entire data set, including both training and validation. And then cross-validation. When cross-validation is used, the sequence of models MK in the previous tree algorithm, best subset selection, forward, backwards, stepwise selection is determined separately for each training fold, and the validation errors are averaged over all folds for each model size K. And then, for example, the best subset regression MK, the best subset size K can differ across the folds. We only use cross-validation to determine the best size K. Then we find the best model of the size K on the full data set. Okay. Next. Shrinkage methods. In subset selection, we selected a subset of predictors using linear regression. I don't think these are important. So, we usually start with the standard linear model, okay? And then, using the values that minimizes the RSS. What is this, bro? And then, ridge regression is similar to least squares, except that there's a consideration of the two norms of the coefficient vector. The tuning parameter lambda is used to control the relative impact of the two goals. When lambda is equal to 0, the shrinkage is ignored and we acquire least squares regression. But when it converges to infinity, the RSS part is much less important than the shrinkage part, and we tend to get estimates of coefficient close to 0. The selection of this tuning parameter can be done using cross-validation. Okay, so the shrinkage penalty is that noting that the shrinkage penalty, i.e. lambda summation b of j squared, is applied only to the coefficients of the variable but not to the intercept. So we'll shrink the variable coefficients because we want to shrink the estimated association of each variable with the response. We do not shrink the intercept because it is simply a measure of the mean value of the response when all x variables are set to 0. Okay, so I guess we don't shrink intercept. Is this important? Y'all think this is important to write down on my cheat sheet? Literally look at it. And I would eat these blueberries, but they're all unripe. So I have to let it sit out for I don't know how long. So I think I'll just write this down in case. Even though I don't know how to apply it. This is the R command. Note that even though X is not standardized, the glmnet function does it automatically. When log of lambda is 10, there are 19 slope estimated, non-zero. Lead category variable when log lambda is -5. League's estimate is around 110. So when log lambda is 20, all 19 slope estimated are non-zero. Okay, years in variable 7. When log lambda is 0, beta hat are years is -25. Huh? Oh, -25 here. Okay. So, according to CV error, at optimal lambda, there are 19 non-zero coefficients. What is optimal lambda? I wrote it here. So, left vertical line is the best predictor. So this is the left vertical line. That's optimal. Okay, and then log lambda is 19. It's 5 here. Is it taking e to the 19th? Let's see. Whoa, that's a big number. It's not e to the 19th. We'll say e to 5.78. Oh, that is 5.78. So e to the, not the slope, but the log lambda's value. Because e to the 5.78 would be 323.7. Okay, that seems close. So when you compute it, just put like e to the log lambda value. Okay, and then trading for cross-validation, then testing, find out the test MSE. The final result is acquired using the selected lambda on the entire data set. My cat is here. No blueberries for you. He wants the blueberries. He wants it so bad. Excuse me, sir. Okay, back to where we were. So ridge regression and regular least squares. Advantage of ridge compared to least squares, regular least squares, is that ridge regression has a smaller variance at the cost of a larger bias. And then the disadvantage has a larger bias, computationally slower. So selecting the tuning parameter, the selection of the optimal value of the tuning parameter lambda used for ridge or lasso is based on cross-validation. We first choose a grid of lambda values and compute the cross-validation error for each value of lambda. And then we identify the lambda that gives the smallest cross-validation error. Finally, we use this lambda to run the ridge or lasso regression on the entire dataset. And we're done. We're actually done. But honestly, some people have said that you have to go over the midterms. Like, both midterm reviews. I didn't do that part. I did try to attempt to review the first midterm, but not the second one. Which makes me anxious, because I should probably do that. But if the final review consists only of these things, then I should be good, because I don't honestly like. Okay. Yes. Here's a mini mock exam. Alright, guys. I think I'll leave this page empty, because I ain't got time to look at midterm number 2. I might regret that, though. I don't know. Okay. How do you say I'm actually prepared? I got a 70 on the whole exam, but he says I got 100% so far. That's basically everything I wrote though. Nothing to do with the midterm. I don't know. I have 2.5 hours. But I think I'll call it there. Alright. Bye guys.